Now let us calculate the expression for carrier concentration in an intrinsic semiconductor. In intrinsic semiconductor, just now we have seen electrons in conduction band, holes in the valence band will carry current. So we have to calculate the density of electrons in conduction band and density of holes in valence band. So the first part is density of electrons in conduction band. So in conduction band, let us take some small energy range dE, that is from E to E plus dE. That is, if suppose this is the conduction band, I am taking small energy range. Let this be E and this be E plus dE with the small range of dE. So in this small range, let Z of E dE be the number of states, the density of states, and F of E is the Fermi function. Then the number of electrons available in that small range is given as dN is equal to F of E into Z of E dE, where Z of E dE is the density of states and F of E is the Fermi function, that which gives the probability of that particular state to be occupied by the electron. This density of states is for these conduction electrons is given as Z of E dE is equal to 4 pi by h cube 2 me star whole power 3 by 2 e to the power of 1 by 2 dE. Here we are considering the energy levels only to the above of the conduction band. Suppose this is the conduction band. This is the minimum energy level of the conduction band EC. The energy levels which are greater than this EC, they will contain the electrons and these will carry the current. So the energy levels which are more than EC only we need here. Less than EC, they won't carry current at all. So those electrons we don't need. So this energy is replaced with E minus EC. So Z of E dE is equal to 4 pi by h cube 2 me star 3 by 2 E minus EC to the power 1 by 2 dE. Coming to the Fermi function, F of E is equal to 1 by 1 plus e to the power of E minus EF by kT. In this, Fermi energy EF, it lies between the valence energy and the conduction energy. As our energy levels is always greater than this Fermi energy, because our energy levels we are considering in the conduction band. So E minus EF is always greater than kT. So as E minus EF is greater than kT, this E power value will be a bigger one. So 1 can be neglected. So as 1 is neglected, it will become E power E minus EF by kT. So that as it goes up, the power minus 1 will become. So E power minus of E minus EF by kT. By multiplying this minus to the inside, so finally our Fermi energy level F of E has become E power EF minus E by kT. So substituting this Fermi energy level and the density of states in our dN equation, we will get dN is equal to F of E Z of E dE. So our F of E is E power EF minus E by kT and Z of E is 4 pi by h cube 2 me star power 3 by 2 E minus EC power 1 by 2 dE. Let us interchange the terms, bringing this exponential term to the last. Our equation will become 4 pi by h cube 2 me star power 3 by 2 E minus EC power 1 by 2 E power EF minus E by kT dE. These are the small number of electrons present in the small energy range dE. We need the electrons present in the conduction band. So let us integrate this dN. As we need the electrons in the conduction band, the minimum energy is the conduction energy level EC and the maximum energy is the infinity. So integrating the above equation between the limits EC to infinity. So integral EC to infinity dN is equal to integral EC to infinity 4 pi by h cube 2 me star power 3 by 2 E minus EC to the power 1 by 2 e to the power of EF minus E by kT dE. Bring the constant terms outside the integration. So it will become to 4 pi by h cube 2 me star power 3 by 2 e to the power of EF by kT. Here EF is also constant our variable is only energy E. That's why EF is also brought out here from this exponentials e power EF by KT. And inside the integration, we are having E minus EC to the power 1 by 2 e to the power of minus E by KT dE. So to integrate this, let us take a new constant as E minus EC is equal to X. Then our dE will become dx and our limits will change from EC to infinity as 0 to infinity. So our equation has become, the remaining outside part is same. Inside this integration, integral 0 to infinity x power 1 by 2 e to the power of minus EC minus x by KT. So this minus EC is again constant. So e power minus EC by KT is brought out. Only the x is variable here. For us, only x is variable now. Our energy terms are converted to x. So again, bring this e power minus EC by KT outside the integration. Our equation becomes n is equal to 4 pi by h cube to me star power 3 by 2 e power EF minus EC by KT integral 0 to infinity x power 1 by 2 e to the power of minus x by KT dx. So to solve this integration, we are using gamma function. So that gamma function, putting the suitable values, as instead of x power n plus 1, we are taking half, right? So that standard integral value is integral 0 to infinity x power 1 by 2 e to the power of minus ax dx is equal to 1 by 2 a root pi by a. In the place of a, we are having 1 by kt. So integral 0 to infinity x power 1 by 2 e to the power of minus x by kt dx becomes kt by 2 root pi kt. This contains all constants. Here we are having 4 pi by h cube 2 me star power 3 by 2 e to the power of EF minus EC by KT into KT by 2 root pi KT. Here we can observe things like, see, KT is there, root KT is there, and here 1 pi is there and root pi is there. So for these terms, power 3 by 2 will come. And already we are having 2 me star power 3 by 2. So let us bring all these terms inside this bracket along with this Planck's constant also. So putting all the terms inside these brackets, we will get n is equal to 4 pi by h cube 2 me star power 3 by 2 e to the power of EF minus EC by KT, KT power 3 by 2 by 2 into pi power 1 by 2. Finally, after putting all these under one bracket, we'll get n is equal to 2 into 2 pi me star kt by h square power 3 by 2 e to the power of EF minus EC by KT. This is the expression for density of electrons present in the conduction band in pure semiconductor. Let us derive the density of holes present in the valence band. We need the holes present in the valence band. Anyway, always the holes present in valence band only. In conduction band, no holes will present. Only the holes will present in valence band. Only those holes we need. Similarly, how we have taken for the electron, similarly here in valence band, let us take small energy range dE, how we have taken that as from energy E to E plus dE. So small energy range we are taking here in a valence band. The highest energy level in the valence band is Vc. Already we know that, we have seen in the previous class. So these number of holes are given with the expression dP, where P represents the holes. So dP is equal to 1 minus of f of E, because f of E gives the presence of the electron. 1 minus f of E will give the presence of hole. So it is 1 minus f of E into z of E dE, where z of E dE already discussed, it is the density of states, and f of E is the Fermi function of electron. 1 minus f of E gives the value of the holes. So similar as like previous, z of E dE is equal to 4 pi by h cube 2 mh star power 3 by 2 e to the power of 1 by 2 dE. But here we are considering the energy levels in valence band. So that's why these energy levels we are taking in the valence band. So this E is represented as EV minus E. And the Fermi function 1 minus f of e is equal to 1 minus of, as we already know, f of e is equal to 1 by 1 plus e to the power of e minus ef by kt. By subtracting this 1 minus of this fraction, we'll get, sorry, actually this is wrong. Here it will be getting this numerator, this denominator here, that is 1 plus e to the power of e minus ef by kt minus 1. So 1, opening the brackets, this minus 1 will get cancelled. Remaining term is e to the power of e minus ef by kt. Where ef is our Fermi energy level and E is the energy level, what we are considering here, the energy levels in the valence band. So this E is always less than EF. So EF minus E is greater than KT. EF minus E is greater than KT. So this E minus EF is less than KT. Therefore, we can neglect these E powers as very small. But neglecting means it cannot be 0. But almost it will be looks like 0. So when compared to 1, this E power can be neglected. Finally, it will become e to the power of E minus EF by KT. So the Fermi function of the holes has equal to e power E minus EF by KT. E power E minus EF by KT. Substituting this Fermi function and the density of states in the expression of holes, we'll be getting dp is equal to 1 minus of f of e z of e dE. So this 1 minus f of e dE is equal to, we got e power E minus EF by KT, and z of e dE is equal to 4 pi by h cube 2 mh star power 3 by 2 ev minus e power 1 by 2 dE. Rearranging the terms, this exponential has brought to the last. And also these are the number of holes present in the small energy range D. To get the total number of electron holes, we have to integrate. The highest energy level is the valence band only. Holes won't be present after the valence band. So the highest energy level is EV and the lowest energy level to the bottom to any place the holes may present. So the bottom energy that will be like minus infinity. So the limits are minus infinity to EV dP. So the same it is represented here. Now bringing the constants out of this integration, we will get P is equal to 4 pi by h cube 2 mh star power 3 by 2 e to the power of minus EF by KT integral minus infinity to EV minus E to the power 1 by 2 e to the power of E by KT dE. As Fermi energy is constant, it is brought out. As done in the previous case, the same, taking EV minus E as a new constant x, minus dE will be equal to dx. So the limits will be changing, as upper limit will become 0, because as E tends to EV, the upper limit will become 0, the lower limit will be infinity. So our integration, only the integration part has become like integral 0 to infinity x power 1 by 2 e to the power of EV minus x by KT into minus dx. So this minus sign is used to interchange these limits from 0 to infinity. So using this negative sign, the integration limits are changed from 0 to infinity. So our equation has become P is equal to 4 pi by h cube 2 mh star power 3 by 2 e to the power of E minus EV minus EF by KT integral 0 to infinity x power 1 by 2 e to the power of minus x by KT dx. Again the same integral we got, what we got in our derivation in the case of electrons. So this using the gamma function, that is equal to KT by 2 root pi KT. Substituting in that equation, and here also the same we got KT and root KT, pi and root pi. So all these are having power 3 by 2 along with 2 mh star, bringing all these terms in under one bracket. So substituting them and rearranging them, finally we got P is equal to 2 into 2 pi mh star KT by h square whole power 3 by 2 e to the power of EV minus EF by KT. So this is the number of electrons present in the, this is the number of holes present in the valence band. Okay, we got the expression for N and we got the expression for P, the density of holes and the density of electrons. But to say in general, because we are talking about the intrinsic carrier concentration. In intrinsic semiconductors, we will be having both the electrons and holes to carry the current. The number of electrons moving to the conduction band is equal to the number of holes generated in the valence band. So this will be equal, and let that be equal to the n suffix I. This is called the intrinsic carrier concentration. So in general, we have to say this Ni. So to generate this Ni, let us take Ni square is equal to N into P. That is equal to 2 into 2 pi me star kt by h square power 3 by 2 e to the power of ef minus ec by kt. This is the expression for n. And the expression for P is the 2 into 2 pi mh star kt by h square power 3 by 2 e to the power of ev minus ef by kt. Here 2 into 2 it is 4. In these brackets, though they are having 3 by 2 except me star and here mh star, remaining all is same. They are brought separate, like 2 pi kt by h square power 3. So 3 by 2 plus 3 by 2 it will become 3. And this me star, mh star to separate bracket power 3 by 2. E to the power of ef minus ec plus ev minus ef by kt. So this plus ef and minus ef gets cancelled. Finally, this will become e to the power of ev minus ec by kt. I think you can get an idea, right? As EV minus EC. As in the previous discussions, we have seen the energy gap, the gap between the valence band and the conduction band. That means here the highest energy level in the valence band is the EV and the lowest energy level in the conduction band is EC. The difference between these two is equal to energy gap. So EG is equal to EC minus EV. EG is equal to EC. Sorry, here I have written V, it is C. EC minus EV is equal to EG. Substituting that here as EC, EV minus EC is there, so minus EG will come. So we are getting Ni square is equal to 4 into 2 pi kt by h square whole power 3 me star mh star power 3 by 2 e to the power of minus Eg by kt. So in finally we got our equation for intrinsic carrier concentration in energy gap terms. So Ni taking square root on both sides. So Ni is equal to 2 into 2 pi kt by h square power 3 by 2 me star mh star power 3 by 4 e to the power of minus Eg by 2 kt. This is our intrinsic carrier concentration in semiconductors. Remember students, in exam, if it is asked, derive the expression for density of electrons in conduction band, means you derive only up to n value. If it is asked derive the expression for density of holes present in the valence band, you go only with the p derivation part. If it is asked in the exam, derive the expression for intrinsic carrier concentration in semiconductors, then you have to derive N, you have to derive P, and also this part also. You have to derive up to this Ni. So Ni is equal to 2 into 2 pi kt by h square power 3 by 2 me star mh star power 3 by 4 e to the power of minus Eg by 2.